Okay, so this should be our last video for 12.1. And before we dive into example 2, I wanted to do a quick recap of our conditions for that first example that we did, making sure we had everything that we needed. So I just wanted to make sure that you had a good chance to see it typed out, because I know my handwriting isn't always the best. So this was back an example or two. Also, I want to make sure that you're familiar with how we interpret our standard error. Here is a kind of sample sentence filler-inner that you can use. This screenshot right here is what you see on the formula sheet on the AP exam. So you can see how they give you the parameters for your sampling distribution, beta, our standard deviation, aka standard error, and that's over here. Like I said, you'll probably never, ever, ever actually have to calculate it, but it is helpful to know that it's there. When you're checking your conditions, I want to make sure you're aware why we check them, not just, what they are, but what's the purpose behind them. We want to check to make sure it's linear, so that there actually is a linear relationship between x and y. If we're trying to, calculate a confidence interval for the true slope, or do a significance test for a value of slope, we want to make sure it's actually linear and that slope applies. For independent, it's okay to make sure that we're sampling without replacement, so that's a 10% condition. Again, if it's from sampling, if it's an experiment, we assume it's independent because of the random assignment. Why do we care about normal? Okay, so for each x, we need to make sure the distribution of y is approximately normal, because we are still using strategies using normal techniques. Equal variance, we want to make sure that for each value of x, the standard deviation of y is about the same. Okay, so that's why we want them to be evenly spread. And then obviously for random, we've been talking about this one forever. We want to make sure we can generalize to the population, or that we can show causation, because we can't do that without that. We've already gone through one example together, and we did a confidence interval. The example we're going to look at now is how to do an appropriate test, how to do a significance test. So let's dive into that. For example 2, we already did example 1. For example 2, do customers who stay longer at buffets give larger tips? Charlotte, an AP statistics student who worked at an Asian buffet, decided to investigate this question for her second semester project. While she was doing her job as a hostess, she obtained a random sample of receipts, which included the length of time in minutes the party was in the restaurant and the amount of tip in dollars. Do these data provide convincing evidence that customers who stay longer give larger tips? So there's a lot presented to us on this page. We do want to carry out an appropriate test, and we'll get to that. But I want to talk about a few things first. First thing I want to talk about is the computer output here. Okay, making sure we can identify everything that is there on the computer output. So this value here is our A, aka our y-intercept for the sample. The value here is B, aka our slope, again for our sample. Some other values that are important. This value right here is going to be our standard error of our slope. Okay. This value of S is going to be the standard deviation of the residuals, so we don't really care about that right now. Obviously, we have R squared. This 1.23 value is actually already giving us our T value, our test statistic. And this P value right here is going to be the P value if our alternative hypothesis is a not equal to situation. So if this was like a less than or a greater than, we would just have to cut that in half. So your computer output actually gives you most of the calculation stuff up front. Now, in addition, we also have our table of values here. We can see the time and the tip that related. Down here on the side, let's make sure we can identify each graph. This first one here is going to be the scatter plot with a picture of the least squares regression line. So here's our scatter plot with the least squares regression line plotted on it. Below that is going to be the residual plot. And the final one, it's graphing the residuals against the z-score. This is the normal probability plot. I highly doubt you'll ever have to actually create all of these for a significance test if this was like a short answer question on AP test. If it was a short answer, they'd probably, like this, provide all of these visuals for you, and you just have to use them and interpret them appropriately. Okay, let's dive right in. We are doing our 4-step process, just like normal, okay? So first step is going to be to state. When you are stating in a 4-step process for a significance test, which is what this is, we need to say what our hypotheses are, define our parameters, and then also say what level of significance. So what we want to do is we want to perform a test of, and then here are my hypotheses. My null is that my slope is equal to 0, that's a beta, versus my alternative. Now, because they wanted to know, or what's her face? Charlotte wanted to know, is there evidence that they give larger tips? Larger tips, if they stay longer, implies that there is a positive relationship in your data. If there's a positive relationship, you would expect to have a positive slope, meaning you would expect your beta, your true slope, to be bigger than 0. Right? A positive value. If it's less than 0, you'd expect a negative association. And then we have to define what beta is. So beta is the true slope of the population regression line relating, and then here's where you insert your context, relating your tip amount, y, to our length of stay, x. And we are doing this at an alpha of 0.05. They did not tell me to use 0.05, but as always, if they don't tell you what to use, that's what you're going to use. That's your default. Now we move into the plan. Let's come up with our plan. If our conditions are met, we need to do, all right, now what's the name of this thing? Well, this is going to be called a t-test for slope. Okay. So if our conditions are met, do a t-test for our slope beta. And now we get the joy of going through all of our conditions, all 5 conditions for liner. For the linear condition, you need to look at your scatter plot and or your residual plot. In this case, our scatter plot does in fact show a weak positive linear relationship between our length of stay and our tip amount. And then the residual plot also shows random scatter about the residual equals 0 line. So what I mean by that, you can see how, scooch this up, there's a random scatter above and below this residual equals 0 line. So you're good to go for your linear condition. The next condition we have to check is I, so independent. This was not an experiment. This came from sampling. So we do need to check the 10% condition. She took a sample of 12. Safe to say there's going to be more than 120 receipts in the population from which these receipts were selected. Also, knowing one tip amount shouldn't provide additional information about other tip amounts. So kind of two things there that we're talking about for independent. And again, if you need to pause this video so that you can write this down, that might be a good thing to do. The next condition is N in our LINER acronym, so normal. This is why we want to look at the normal probability plot. Our normal probability plot shows us that it's roughly linear, which is what we want. Okay. I should say the normal probability plot of the residuals is roughly linear, so that's going to satisfy our normal condition. E stands for equal variance. Again, looking at your residual plot, it shows a fairly equal amount of scatter. There's what, 1, 2, 3, 4, 5, 6 above, 1, 2, 3, 4, 5, 6 below, about equal scatter. And then last but not least is our random, and our receipts were randomly selected as it was stated in the problem. So all 5 of our conditions have been met, which means we are good to go for doing our calculations. Now, the calculations shouldn't be too challenging here. We take our sample slope and we subtract what we think our true population slope is, which came from our null hypothesis, which was 0, right? We were saying, what if there is no linear relationship? And we're testing to see if there is a positive linear relationship. Standard error of the slope goes on the bottom, which came from the computer output. So you didn't have to do any math there. Okay. Now, when you divide those two values, you get a test statistic of 1.23, which again, we saw from the output above. Degrees of freedom, when you have linear, is always going to be n minus 2, which is different. It used to be n minus 1, and then for chi-square, it was completely different. So our degrees of freedom is 10, because there were 12 pairs of data, so 12 minus 2 is 10. Now, the computer output is always for a two-sided test. So if you're going to use the computer output, you have to divide it in half. Or you can use your TCDF. That's another great option. Make sure you have your lower value, your upper value, and then your degrees of freedom at the end. And either way, you should get about 0.12345. The only thing that's left to do is to come to a conclusion. That is a pretty large p-value. So since our p-value is in fact larger than our alpha, we are going to fail to reject our null, which means we do not have convincing evidence that parties who stay longer at buffets leave larger tips. So we can't conclude that my slope is positive, which in relation to the context means we can't say that the longer you stay, the larger the tip is going to be. All right, if you need to rewatch this, please do. In class, we're going to be doing more practice with these. The hardest part is probably going through all of the conditions. The calculations aren't too tough. So yeah. And then we will get to section 2 and the very last section of statistics here in the next day or so. Thanks, guys. I will see you later.